Welcome everybody to our webinar today, Focus on Recovering Signals in Optical Experiments, presented by Zurich Instruments and hosted by Photonics Media. My name is Sarah Weiler and I'm the Photonics Media Webinar Coordinator. I'd like to introduce today's presenter, Dr. Claudius Rieck, Application Scientist at Zurich Instruments. Rieck will be speaking today on optimizing optical and photonic signal recovery as a follow-up to Zurich's previous webinar on this topic, Optimize the Signal Acquisition for Optics and Photonics Measurements, which is available on demand on the Photonics Media website. Today's webinar gives us a deeper look at the topic based on feedback from that last webinar. If you have any technical issues during this webinar, please log out and log back in to rejoin. A recording will be available on the Photonics Media website shortly after the presentation today. Everybody who registered will receive a link to that recording, so if you have a colleague who couldn't join us, please let them know that the recording is going to be online. We encourage you to ask questions at any time throughout the presentation. Just type it into the chat box on the side of your screen, and we'll respond to as many as possible at the close of the presentation. And with nothing further, I'd like to introduce our speaker, Dr. Claudius Rieck. Welcome, Claudius.
Thanks for a great introduction, Sarah. Very happy to be here the second time. And yeah, let's jump right into it. So we want to focus today on how to recover signals in optical experiments, optical measurements. So first of all, the question, what is actually measured in photonics? We have a few examples here. First of all, you have things like linear spectroscopy, you measure absorption. Terahertz time domain spectroscopy, you measure in the end the polarization state change to map out the electric field of your terahertz or mid-infrared transient. In SRS microscopy, or for example, you measure the pump pulse loss. And laser voltage probe is a different possibility to measure the reflectivity. So very similar than the linear spectroscopy. Now, what you have in addition is not only what is measured, but the question is, how big are those effects? How big is the signal which we have to measure actually? Now, in linear spectroscopy, we have easily have to measure changes of 10 to the minus 8 of change in transmittance. A very similar number is correct for the terahertz time domain spectroscopy, where you can also very quickly go down to a delta E over E of something like 10 to the minus 8. And for SRS microscopy, I put now 10 to the minus 7, but as the people who work on this topic know, you can also go much lower. And this is precisely when you have to measure very carefully, because you want to recover those small effects. In the last case, for example, SRS microscopy, you want to do it on top of a big signal. So there's something kind of flooding your entire signal input stage. Or what also can happen, it can be buried very deep in noise. So on the right-hand side, you see those two options depicted. Here we have tiny signal on top of a big offset, or we have to search for something very deep in the noise. And the main goal there is always to preserve the information content. Now, the last time in the webinar in June, we made a short poll asking for what was most useful for you, because this is what we want to expand on. This is where we want to provide more information, and you can see the results there on the slide. We got clearly the response. It's the working principle, so really the details on how you measure, how you acquire signals. And this is why we said, okay, let's focus on this part. Also maybe combine it again with the comparison of the lock-in amplifier versus the Boxcar averager to provide the best output. I can give you already a heads up. Feel free to put in your questions into the question section of the GoToWebinar software. We will try to answer them, as Sarah mentioned. And very important, keep in mind, there will be a poll at the very end, again asking what was most useful. This will allow you to steer a little bit what we will cover in the future. But now, what can you expect today? We will address questions, for example, like why signal recovery is necessary for optical signals. We already motivate this to quite some extent. What is the effect of different instruments settings on the measurement? So we will have different examples. We will show how to, for example, the filter response will change the measurement, or what the measurement bandwidth means. And of course, also how relevant are typical instrument specs for optical measurements. We'll also comment on this. Now, why is signal recovery necessary for optical signals? I already motivated a little bit, but here I want to stretch this to the limit. What we have in optical methods is the possibility to provide highest measurement precision. Here you see two examples. One is to measure pretty precise, minute length changes. You will immediately recognize the LIGO experiment. Also, this was optical measurement. Or we have the mapping of ultra short pulse, so-called attosecond pulse, on the right-hand side, which is also mapped out using an optical measurement technology. In the end, we need to capture the information there, convert it into an electronical signal, and preserve the information content. Now, this is where we come into the game. Zurich Instruments has a clear mission. We want to provide the best-in-class dynamic signal instruments for advanced R&D labs. The question is, how do we do that? We take, in the end, off-the-shelf hardware. We combine this with software to prepare to make our instruments. Why do we do that? Hardware, everybody can build buy basically the same components. And some of our customers and users do that. They build their own instruments. Still, if it comes down to the software, if it comes down to the signal processing performed on the FPGA in the device, done with ultimate performance, this is where we can bring in all our know-how and our experience, create efficient workflows, optimize the user interface and APIs to make the time from when you want to do a measurement until you have it done much faster. And we even add value over time. So in this, how we create lock-in amplifiers, Boxcar averagers, and a few other things, but these are the two on which we want to concentrate. But now we come to a very important question. What do you want to do in the end? What do you want to me to focus on? I already mentioned what I would mainly be, but of course I still can kind of emphasize one thing or the other thing more. So Sarah, can you please start the poll for us?
Absolutely. So I'm going to launch the first poll. As Claudia said, the question is, what should we focus on? Possible answers are lock-in amplifier and Boxcar average working principles, effect of instrument settings, or relevance of typical instrument specs, e.g. signal input noise. I'll give you a couple of seconds to respond. All right, I'm going to close the poll and share these results. So what should we focus on? 44% of you said lock-in amplifier and Boxcar average working principles, 29% said effect of instrument settings, and 27% said relevance of typical instrument specs, signal input noise. Thank you very much. I'm going to close the poll.
Okay, unfortunately now I could not see the poll results. Sarah, could you quickly tell me what was the highest one? Sorry, I missed that.
Oh no, that's fine. The highest one is 44%, and that is lock-in amplifier and Boxcar average working principles.
Okay, so perfect. Great, thanks a lot. Thanks also for participating in the poll. This means we will focus on this topic, and let's jump right ahead. What do actually typical systems look like? So we can always simplify typical optical signals. We have always 4 functional sections. So we have typically a source, we have an experiment, and a detector and a signal. You see 3 completely different examples the middle one focusing on spectroscopy, linear spectroscopy, the other one on terahertz time domain spectroscopy, and the third one going more into the middle infrared detection. But all of those, you can identify very clearly those 4 components. And this is why we will focus only on the signal analysis at the very end. But of course, there are some important inputs from those 3 first stages. But we can really kind of not go in detail there, but take them as a given. We focus on spectral integrating detectors, for example, photodiodes, etc. Now, where is the actual information in the signal? Now, I depicted here 3 different typical cases. You always have a certain parameter variation, which leads to a change in the signal. On the top side, on the top example, you have, for example, a change in the amplitude for a certain duration. Those are the those are the signal parameters which we want to measure actually in the very end. In the middle one, we have, for example, a sinusoidal modulation. There we have an amplitude, and in addition, we can measure a phase. And of course, you can have kind of a mixture of multiple of those parameter variations. This example at the very end, where you then have a mixture of sinusoidals or different functions. Now, the question is, how do a typical signal look like? And there I want to get kind of a few basics very clear. So again, we have the parameter variation, which leads to kind of our signal. This is supposed to be the step response here. This is our signal. And we want to now have kind of always this, we want to have an optimal signal to noise ratio. What does a signal to noise ratio mean? It means we can measure this step response very clear and discriminate against some effect which comes from noise. On this signal, it goes fairly well, but if you imagine the signal would be 10 times smaller, it might be already buried in the noise. So what do we want to achieve? We want to capture all signal components and suppress the noise. What means? We kind of want to digitize and average. So this is also the first step. What every, I would say, normal or modern lock-in amplifier does. First, it digitizes the signal, and it digitizes the signal with a sampling rate, which basically defines over the Nyquist theorem the maximum input bandwidth. It defines how fast we digitize the signal. In addition, we have the bit depth of the analog to digital converter. And this defines the granularity. The granularity is 2 to the n bit. And as you can see on the right-hand side, it clearly maps out the signal depicted in red way better if I have more bits. Now you could say, okay, great, let's go for whatever, 20, 40 bits. This is not so easy if you go to very fast frequencies, because there just the electronics, the hardware does not exist. And this is why we have to be a little bit careful and have to consider the so-called dynamic range, which we have based on this digitization. The dynamic range describes kind of the smallest possible signal that can be measured for a given input range. So to stay with the example on the right-hand side, it would be kind of if I have one step, so 1 bit in signal this high, I would be able to measure it. If it's below, I would see 0 because the digitization will show nothing else. An example for 12-bit, for example, is 2 to the 12, and unfortunately this is a wrong number. Of course, 2 to the 12 is 4096. I'm not sure why this got mixed up. Now you could say, okay, but this means we are kind of limited to something like 4 to 5 orders of magnitude. This is not entirely correct. This would be if you rely on the dynamic range of the digitization only. But in the moment when you bin the samples or you do additional signal processing, like for example, averaging, you can increase this much more. And on the lower right-hand side, you see an example where we have something like 120 dB dynamic range, or you can even 120 dB dynamic range. Now, for applications where you want to go beyond that, so where you want to go beyond those 13 orders of magnitude in power, there might be additional tricks required, for example, using balance detection, because this already allows you to minimize the input range to a relevant measure. Okay, now we have the digitized signal, and so we can have a look at the noise. In the beginning, the pure digitized signal exhibits noise from kind of the entire noise equivalent power bandwidth. I depicted this here for a certain filter, and the noise equivalent power bandwidth is kind of the rectangular filter bandwidth. If you would, so that the integral over this rectangular filter and the real filter depicted in blue is the same. Now, for a pure digitized signal, this means the entire noise of the entire signal going all the way up to the Nyquist limit is in the signal and is on top of the signal, so contributes to our noise. And very important to keep back in our mind, the signal itself is filtered with the so-called cutoff bandwidth. So the -3 dB bandwidth, which is always a little bit more narrow. So what does this mean if we think, for example, about the real noise sources and a real experiment? So we always have different noise sources, noise contributions. The most prominent, most likely, is the 1/f noise, which comes often from the detector noise. We have a shot noise, which comes typically, the shot noise is a quantum limited noise. And this is a white noise contribution spanning over the entire frequency range. And we have some noise spikes, of course, which are due to, for example, technical pickup and so on. Now, we mentioned at the beginning, okay, we can just average our noise to increase our signal to noise ratio. But averaging is nothing else than low pass filtering. And now if you look on the right-hand side, here we depict a low pass filter. Unfortunately, a low pass filter will be always at the place where we have the highest noise contribution, close to DC. So what we want to do, we want to shift it out into the regime where we have less noise. And now let me quickly also combine this with the signal input noise, because often we are asked, yeah, I want to buy a lock-in, maybe I should really go only for the very best in signal to noise, in signal input noise. Sorry. In general, this is always a good idea because noise adds up in quadrature. So this means noise always piles up, and with the less noise you start, the better. Still, your goal should be always that you're above the signal input noise, for example, with your inherent detector noise, or ideally, you aim for a shot noise limited, so a quantum limited measurement, because then you cannot go any better. And then maybe the signal input noise could maybe be not the dominating noise in your application. This is what you should for sure aim for. Now, going back to the how we get to this region where we can achieve a quantum limited detection into the white noise regime, we want to modulate the signal. We want to shift the signal into this regime, and we do that by adding a modulation, typically between the source and the experiment itself. Then afterwards, we analyze the signal with a lock-in amplifier or the Boxcar average method, where we use the information which we put in during the modulation. And we choose the modulation frequency, of course, to be in the low noise regime. On the left-hand side, you see now 4 different filters depicted. 4 different center frequencies of the filter. The filters are identical, and you see immediately the one at DC, this is the blue one, has a huge amount of noise. The one at 500 Hertz, modulated at 500 Hertz, is already better, and it improves. So I would say somewhere between 5 kilohertz and 100 kilohertz. Here we have roughly the corner frequency. We do not see a lot of change. So this is the frequency regime where we want to aim at. How do we do the modulation? Of course, there are different typical methods. We have, for example, a chopper wheel with acoustic optic modulators. We have electro-optic modulators, and in the end, we also have already modulated light sources, for example, pulsed lasers. Now, what the modulation defines is the modulation frequency, of course, this we mentioned at the beginning, but it also defines the modulation function. For example, a chopper wheel with a nicely matched beam diameter will give you a nice sinusoidal wave. If the beam diameter, though, is much smaller, it will basically give you a rectangular modulation. So you have the fundamental frequency and harmonics on which you could measure as well. Of course, something very similar is true also for acoustic optic modulators, electro-optic modulators, where you can really use a certain modulation function to modulate your light beam. Where it's slightly different, we will come to that, is typically mode lock lasers or pulse lasers. There we have a super short duty cycle, and there you can basically switch them on or off, of course, or modulate them to some extent on top. In the end, the modulation method defines the achievable signal to noise ratio, because depending on the frequency you aim for, and therefore also the measurement speed. And of course, to do that, what you need is you need to choose the right lock-in amplifier to go with this frequency. I already mentioned the different frequency regimes where we can modulate, and on the right-hand side you see we have kind of the different platforms we use: the MFLI, the HF2LI, the UHF-LI, and they are always tailored and built for a specific input bandwidth. And of course, also you should choose then a lock-in amplifier which fits in terms of input noise and dynamic reserve or dynamic range, which we discussed earlier. Therefore, also you have a few more tool sets which you can have in a modern lock-in. For example, the data acquisition already built in, or a PLL and the PID. But now let's jump into how the whole thing works. What you ask for in more detail, and we need all the basics for what we are looking at now. So, how does the lock-in amplifier work? First, we have the signal input, which is depicted here as a slightly noisy signal which goes into the input signal. We multiply this we use the analog scheme, but of course all of this is done in the digital domain, so it's a multiplication with the reference signal, and then the filter used afterwards is similar then to a bandpass filter. You see this depicted on the lower right hand side. So there is the combination of the multiplication with the reference frequency defines the center of the bandpass filter, and the low pass filter bandwidth itself defines the cutoff frequency in the end. And the same thing is defined over the so-called time constant. The time constant is the time until the first order filter settles to 1 over E, because it's an exponential filter. This is why it's the definition, and it's a very typical setting used in lock-in amplifiers. Of those first order filter, we can cascade multiple ones. Therefore, we can improve our filter function in terms of filter steepness, so we can make the slopes more steep. This is the filter order. Now let's have a look with a small application example to motivate what you will look at. So here we suggest to use something like a tunable diode laser spectroscopy, so linear spectroscopy. We sweep the laser wavelength. The gas absorbs some photons depending on the actual gas concentration, and the laser beam is afterwards detected on a photodetector, and we analyze the signal with the MFLI. So the MFLI will continuously kind of sweep the signal, and we have to analyze then the signal depicted over time and optimize the SNR. Don't worry, I will not do it. I did the measurements before, but it's important to have an idea what we see. Now, how does the filter actually affect the signal? The filter bandwidth defines the measurement bandwidth. And this is what we are aiming for. Often, even if we go, for example, for microscopy applications, there it's key to have a broad measurement bandwidth so that you're able to measure to perform your experiments fast and capture your images quickly. The measurement bandwidth I already mentioned goes inversely proportional with the time constant Tc. And on the right-hand side, you see those different examples depicted. So if you, for example, enlarge the time constant, you see that the input signal, which is the step function, will be smeared out a little bit for a first order filter. And the lower you put your the lower you take your measurement bandwidth, the more it will smear out in the time domain. In the frequency domain, though, the filter function gets more narrow, which means it will acquire less noise. So what does it mean for the signal? On the bottom, you see 3 examples depicted. On the left-hand side, you see a 50 kilohertz bandwidth for the measurement I did there. And you see a pretty noisy signal. Well, still, we can already see 2 distinct peaks. We have the 10 kilohertz signal. The signal looks way smoother. If we compare kind of the ratio between the peak of the the peak of the peaks doesn't make a lot of sense, but this is what I want to say. The peak of the peaks compared to the noise baseline, we see this is very comparable, but you would be able to see minute changes on top of it, or as shoulders, for example, because you have way less noise. To go shrinking the bandwidth even more, we end up with the example at 2 kilohertz, where we smear out already the features. So in this case, we would not see some features, and the signal gets already pretty small. So we start also averaging out the signal, which what we don't want, of course. So the ideal choice would be the one in the middle, 10 kilohertz. Now there is a different possibility to optimize the filter. And this is the filter order. The question is, how does this affect the signal? Again, I mentioned we have the first order filter, and we can cascade them. And on the right hand side, you see 4 filters depicted with the actually same filter bandwidth, only with different orders. You see in the frequency domain, kind of the 3 dB point, minus 3 dB point is precisely on top of each other. But then you see that the higher the order, the steeper the frequency domain. And this means the noise equivalent power bandwidth gets smaller, and therefore you have less noise in the higher order filter. It is a trade-off though, because you can also see in the time domain, you smear in the same order of magnitude, but you also, in addition, add a delay. And therefore, we have kind of 2 guidelines on how you should choose the order. It should always be as low as possible, but you should always choose it in a way that it suppresses additional noise, spurious noise or spurious signals. And on the lower right-hand side, you see this depicted. You see some additional signal leaking in this measurement with a third order filter, and in the eighth order filter, you see that that this is not there anymore, so we have a much cleaner signal. Now, of course, we have kind of a different already two parameters. Now the question is, how can we optimize the parameters? And there is a way how to do it. For example, one way is we have a given measurement time and we want to achieve the best signal to noise ratio. Now, what we need to define in addition is the desired accuracy which we want to achieve. So from this initial step response, going from 0 to 1, to what extent we want the filter to settle after doing the measurement and moving, for example, to the next step. Because this defines, for example, how deep our modulation depth can be and so on. So, for example, let's say we want to go for a 95% accuracy. This means we would have to select a second order filter, which you can read from the table on the lower left hand side. Now, why is this? The point behind this is what I depict on the right. I depict filters with the identical noise equivalent power bandwidth. So in a scenario where you have a white noise floor, all those filters would exhibit the very same noise, but they would settle to the desired accuracy with a different speed. In general, we can say lower order filters start settling faster, but to approach the final value, higher order filters are better. And you see that in the beginning, the first order filter is clearly the fastest, but at some point, it is overtaken by the second. And if we look into the inset, if we look at whatever 95 or 98, 99% accuracy, there even the higher order filter kind of overtake those. And based on this, we can select the best filter. So we say, for example, 95% second order, and now we go and calculate the filter bandwidth, which we need to go for the desired measurement time. In the example of typical scanning microscopy, you would take the pixel dwell time, which you calculate from the overall time which you want to have for capturing one frame, and then you go for it. Now, you can just put in those the measurement time, the filter order factor, which is specific to each filter, and the accuracy factor in this formula, and then you can get the right filter bandwidth. To show you that this really has a big benefit, I want to show the images on the right-hand side. On the upper image, you see that there's some noise, but in general, the contrast, I don't highlight, I think you can see it better. The contrast is pretty good, and we don't have smearing. Smearing means, sorry, not smearing, crosstalk. So you have pixel crosstalk, which is due to this slow settling of, for example, a lower order filter. Somebody wanted to be fast, taking the lowest order filter, but due to the smearing, you would always start blurring your entire image, and this is why the lower the image on the bottom does not look as appealing as the one with the optimized filter setting. Now, let's jump to a slightly different topic. We covered now the filter functions of the lock-in to a very good extent. Now, what about if we have pump probe techniques? Pump probe techniques like, for example, visible pump, near-infrared probe, terahertz time domain spectroscopy, which is also a pump probe technique, or nonlinear microscopy. So there, we have a special situation because we have two pulses where the pump pulse typically imprints the signal on the second pulse, the probe pulse. And then we analyze the probe pulse. And what we do now is we change kind of the delay between those 2 pulses, and therefore we have an actual temporal resolution defined by the signal, by the short pulses themselves. What means if we send those signals onto a photodetector, we don't have a nicely sinusoidal wave, but we have a signal with a super short duty cycle. And for example, if we take a pulse picker and kick out every second pulse, as we did on the lower right-hand side for the pump pulse, then this means we have kind of a super short, super low duty cycle signal which we want to analyze. Now, how do we do that? We analyze it, for example, with a lock-in amplifier and a boxcar averager. Now, for a boxcar averager, the overall schematic is very similar. Again, this is not analog, but it's really digital signal processing. So also here, in the lock-in amplifier, we multiply our input signal with a sinusoidal reference frequency. In the boxcar averager, we multiply it with kind of the boxcar windows, which can have a very short duty cycle. So this short duty cycle reference signal. Afterwards, we also use a low-pass filter in the lock-in. We discussed it already. It's a digital RC filter, and on the boxcar averager, it's a non-moving average filter. Now, what does this mean on the actual signal? On the lower left-hand side, we depicted a time domain signal. So in yellow, you see the low duty cycle signal from our detector. And on the right-hand side, you see the frequency domain. And you see the signal is confined in a super short amount of time. And therefore, it spreads out in frequency over the entire detection bandwidth. Now, what a lock-in amplifier does, it captures precisely one harmonic. And this is where we can immediately see there is more information which we can gain there. And this is what the boxcar averager precisely does. So in the boxcar averager, I depict here different boxcar window sizes. And the smaller they get, the further they span out in the frequency. And the broader the detection bandwidth is. Again, this is kind of an ideal solution for our pump probe measurements, where we want to get precisely the signal on every other pulse. Now, every other pulse means we would kind of neglect the pulses without a signal. That's what we don't do. What we do there is we use a so-called baseline suppression window. And now the boxcar averager gets even a little bit more similar to the lock-in amplifier. So again, we have every second pulse with our positive boxcar window and every other pulse where we have a negative boxcar window. What do we achieve with this? What we achieve there is we basically compare one pulse to its successor. And this we do kind of over and over again and average over those. And this has the big advantage that on the right-hand side in the frequency, the DC component drops out. And remember, at the very beginning, we saw that the DC component has the highest noise. The higher harmonics or the harmonics have typically less noise because they are in the regime where we have less amplitude, less noise. And now let's also have a look at how the filter settings for the lock-in amplifier and the boxcar averager compare, because they already do something fairly similar at that point. The lock-in amplifier, we already discussed quite a bit. The signal settling is nonlinear, and the settling depends on the filter order and on the settling ratio, the settling or the filter bandwidth. On the boxcar, though, the signal settling is linear. So this is this red straight line from the 0 to the 1. Now, it is never fast or almost never faster than the first order filter if you compare it if you want to measure with the same noise equivalent power bandwidth. but you can tune it in a way that the Boxcar kind of overtakes a higher order filter of a compared lock-in. And there is a big advantage there, mainly if you want to go to very high accuracy, so to very high settling accuracy of the step response. If you want to go, for example, for 99%, you have to wait for the 8th order quite some time to settle. The Boxcar, though, is kind of immediately at 0 because it has this linear settling where you're just there at some point. And therefore, you can, for example, avoid smearing or pixel crosstalk in microscopy measurements. And this is also kind of the last example to show you that this is not pure theory, but this can be really used. Here we have example measurements where lock-in amplifier and a Boxcar average were compared. There was a scan over the entire image, and each pixel is the data for each pixel is acquired. Kind of wait for a certain time, and then we go to the next. And if you now compare the pixel dwell time of the lock-in amplifier and a Boxcar measurement, you see that there's more than a factor of 2 in between, although the two experiments have the very same signal to noise ratio. And therefore, in the end, you can achieve a speed up to video rate images more easily if you, for example, go for a Boxcar approach than if you would stick only with a lock-in amplifier. Still, of course, in the end, we have to discuss the details of each application, and this is where we are also very happy to help. Now, I hope what we learned today is how lock-in amplifier and Boxcar averages work, how the filter settings affect the measurements, and how to choose the best filter settings. And I hope we could also learn when the signal input noises may be important or maybe not so important. It's important if you rely on the signal input noise only, but if you have, for example, a huge excess noise due to your detector, it might be not that relevant. And of course, dynamic range is also very crucial if you want to measure very tiny signals, for example, on top of a big other optical signals. And now it would be very helpful for me to know what was most helpful for you, and maybe what you want to hear also more in a future webinar. Sarah, back to you.
Sure. So I'm going to launch the second poll here. The question, everybody, is what was most useful for you? You can select one answer. So the first is lock-in and Boxcar working principles. The second is impact of specific settings onto measurements, relevance of typical instrument specs, or applications examples. I'll give you a couple of seconds to respond. All right, I'm going to close the poll now and share those results. So the question again was, what was most useful for you? 42% of you said lock-in and Boxcar working principles. 34% said impact of specific settings onto measurements. 3% said relevance of typical instrument specs, and 21% said application examples. I'm going to close that poll now. Thank you, everybody.
Yeah, also thanks from my side. I'm not entirely sure if my screen is now shared because it looks different from my side, but I think all is
Yes,
fine.
we can see your slides.
Perfect. Can only not advance it. Now it should be possible again, no?
Yes.
Okay, perfect. Now we come to maybe the most important part of the entire webinar, the Q&A session. Sarah, I'm curious, what are the questions?
Absolutely. So we already have a bunch in here, but everybody, if you haven't already asked a question, feel free to enter it into the chat box on the side of your screen. And just a note, we're going to be following up on all questions from today. So if we don't get to it, don't worry. So Claudia's first question for you, what is a good starting point to optimize the filter order?
As I showed during the presentation, a really good suggestion is always to start with the accuracy level. Think about the accuracy level, what you want to achieve, and don't say, yeah, I want to go for the maximum. This is typically not the best choice. So it's this side. So really think about, okay, can I be quick if I, for example, measure with an accuracy up to, let's say, 90% or maybe even lower, and then use a lower order filter and have a fast measurement speeds to do the first measurement, and then refine, because typically it's an iterative process. You adjust the filter order a little bit, then you optimize the filter bandwidth, because every signal is slightly different, and you need to look in detail on how to do it. But what I can say, what is very typical, a very good starting point for typical step scan measurements, for example, is always, I would say, second or third order filter.
How do you determine the frequency and the amplitudes of the reference signal in lock-in amplifiers?
This is a really great question. I would like to go back to the slide. So what is of course of high relevance is at which frequency we want to detect, and this is only relevant if not the lock-in itself provides the reference signal. So what we take, if you, for example, have a chopper wheel, we take the input of the chopper wheel, we use a PLL, locking an internal oscillator of our lock-in to this external reference signal, and then ensure that the reference signal is so the reference signal with which we multiply our input signal is super stable in amplitude and also in phase. And yeah, this is how it works internally.
Could you provide a reference for the detailed theory of lock-in and boxcar averagers?
I'm not sure how deep the theory should go. I think a really good starting point is for sure our white paper, lock-in amplifier principles, or also our YouTube videos where we explain those points and where we also go fairly deep into the math. And not to forget also our manuals, which you can download for free directly in the signal processing section. I think you will find a lot to start with.
For the boxcar averager to be useful, do you need a photodiode that is fast enough to see a short pulse from a laser?
Oh, amazing question. The answer is, of course, yes and no. The photodiode has to be fast enough to see a pulse, yes, for sure, but it does not have to be so fast that you can capture the entire bandwidth of the filter of the laser pulse. This will never work. Imagine you use a 100 femtosecond short pulse, then you would need to have several almost a terahertz of bandwidth. There's no electronic which can do that. So what you will do is you will use a slightly slower photodetector. Therefore, the photocurrent from the laser photons impinging on the photodiode will be slightly smeared out, and you will see basically the response function of your photodiode. But the integral in this of this short pulse will be precisely proportional to the intensity of your laser pulse, and this is why it works. And you should always pick the photodiode, or your detector can be also PMT, for example, with a bandwidth which is a little bit slower than the actual measurement instrument coming afterwards, because otherwise there might be signal components which you lose because you cannot detect them with your detection electronics.
All right, thank you. When is boxcar a better choice over lock-in and vice versa?
Let's start with the lock-in, because this is super simple. A lock-in is always a great starting point. In the moment when you don't see, for example, a signal on an oscilloscope or something like that, modulate your signal, put a lock-in there, and it will improve your signal to noise tremendously. This is also due to the fact that modern lock-ins will give you amplitude output, a phase output, and it will immediately find, for example, the right reference frequency and the reference phase. With the Boxcar averager, you can gain typically on low duty cycle signals. Interestingly, also, if the duty cycle is approaching almost kind of a rectangular form, but you have to kind of put more information into it, where you have to put only the frequency and the phase into a lock-in amplifier. You have to put the repetition frequency as well as the position and the width of your Boxcar window into the signal detection process. But precisely due to this additional information, you can benefit afterwards. So I would always suggest start with a lock-in, and if you want to go for ultimate performance, maybe call us, double check, and we can assess if a Boxcar is a better choice for you.
Can you elaborate a bit on why and how balanced detectors are better than lock-in amplifiers for some cases?
We have to be a little bit careful there. Balanced detector is a detector. Lock-in amplifier is a certain analysis technique. What a balanced detector does, for example, it has two inputs, two optical inputs. On one, you send the signal, and on the other, for example, you send another laser beam, which you pick up before your experiment right after your laser source. What happens then, those two optical inputs are basically subtracted. This is why it's called balanced in the detector itself. And as a result, you only see the difference. The benefit is there. If you have, for example, a noisy laser, both your inputs would go up and down in the same way, and you would not see that as a signal, because only the difference between those input signals matters. Now, this helps you to get rid, for example, of a really huge offset, which you have if you only detect a very strong laser beam on a photodiode. Because then splitting the same laser beam basically in two, your signal would be kind of zero. And this is where then the lock-in amplifier combined with a balanced photodetector is super powerful. And this is typically also the setup in which you can very, very quickly achieve a quantum limited, so a shot noise limited detection. So they both go in parallel. They are not, it's not either balanced detector or a lock-in amplifier. It's more first start with a normal photodiode and a lock-in amplifier. And if you need more dynamic range, for example, then implement a balanced photodetector to allow to go even deeper into the noise with your lock-in amplifier afterwards. In any case, you will need the lock-in amplifier to do the detection.
What influence does it have if the modulation of the signal is square versus sinusoidal?
I have to quickly think how I answer this in the best way. So first, what a square wave means. A square wave means if you make the Fourier transform of it, you will see kind of you have a fundamental frequency, and then you have the harmonics of this frequency. This is what basically build up the kind of nice shoulders of the rectangular signal. What means in the moment when you have a rectangular modulation, you do not only have the signal in one fundamental harmonic, in one fundamental frequency, but also on multiple harmonics. And this allows you to do, for example, sometimes even more precise phase measurements, because the phase detection is more sensitive, for example, at the 10th harmonic. And interestingly, it can even help you to get more signal in your fundamental frequency, because if you remember the Fourier series of the rectangular function, there the fundamental is kind of even more than one, because the peak gets kind of counteracted by the harmonics, And this is so this is even a trick how you can have more signal if you go for a rectangular modulation. So if you need a little bit more signal, this would be an idea to go for.
All right, thank you. I'm going to ask you a couple of more questions. You have way more than that, and I just want to remind everybody these are all going to be followed up on. So, how do boxcars compare to lock-ins when demodulating at several harmonics?
So this is a really great question, because I will just quickly jump to the slide to answer it. So I assume the question aims at the harmonics which I show in this image. And yeah, the lock-in can detect the first harmonic. Maybe it's a user of one of our instruments, who knows, we can even detect up to 8 harmonics. So what you can do, of course, you can take a lock-in and you can detect not only the first harmonic, but also the next, another one, and so on. Now, what the Boxcar averager can do, though, is the Boxcar averager can, because of the different filter function, capture signal immediately from span over multiple of those harmonics, and you can theoretically, no, not only theoretically, you can go, for example, to capturing the signal from 1000 harmonics very easily. Assume you have a 1 kilohertz system. This would mean you only need kind of the measurement bandwidth up to a megahertz to capture 1000 harmonics. And this is what would never work that easily with a lock-in amplifier. But for up to, let's say, up to 8 harmonics, you could do it also with a lock-in amplifier, yes.
All right, I'm going to ask you one more question. Is there an easy way in the Lab 1 software to integrate the Boxcar signal for PDs, which are too slow for ultra-fast pulses?
We would need to look into the application a little bit more in detail, need a little bit more information. But in general, I would say yes, it goes in the direction of what I explained before. Typically, you have a photodiode which is a little bit slower, then you average over this entire response of your detector, and you will get your signal there. But yeah, maybe this is a good idea to follow up on this question. Write me an email, and hopefully I can then, with more information, answer more in detail.
Yes, thank you very much, Claudius. Thank you, everybody, for all of your questions. I'm going to close the webinar now, but just again, a reminder, all of your questions will be followed up on, and you're all going to receive links to the recording of this webinar. In addition to that, I'll include the link to the previous webinar in that follow-up email. So look for that in your inboxes in a couple of days. So one more thank you to our presenter, Dr. Claudius Rieck, application scientist at Zurich Instruments. And thank you everybody for participating with us in Focus on Recovering Signals in Optical Experiments, hosted by Photonics Media. Goodbye, everybody.
Thanks, bye.